another session of the fluid mechanics one. Now today we are going to start with a new article, that is hydrostatic pressure and the stability of gravity dams. Majorly the gravity dams, it is defined as when the structure retains the water by its own weight. Okay, remember this. When the water is retained by a structure by its self weight, they are known as the gravity dams. Okay, now here I have considered this example of the gravity dam with a vertical wall BC, with a vertical wall BC here. So B and C is a vertical face here. Okay, and AB is a incline, AD is a inclined plane, AD is a inclined face of the dam. Okay, so you must have seen the dams at various locations. So this is let us say this is A, B and C, D. This is the gravity dam. Consider the figure which shows the cross section of the masonry dam of a trapezoidal section. Let us say ABCD is a trapezoidal section here. Okay, the top and the bottom widths are A and B respectively. Let us say this is the top width is A and bottom width is B here. Bottom width is B here. Now let H be the height of the dam. So H is the height of the dam here. H is the total height of the dam, whereas small h is the level of water surface level at the upstream side. Okay, so let H or height of water impounded be H, small h. Okay, consider the unit length of the dam. Always consider the length of the dam as a unit length of the dam. We consider the dam length in slices, and each slice is composed of 1 meter while estimating the weight of the dam. Okay, now consider the unit length of the dam. Okay, so area will be B into 1. Okay, because we take length as 1, so B into 1. So the forces acting on this part of the dam as follows. So weight of the dam is equal to W, okay, specific weight of the masonry, into A plus B upon 2 into H. Simple trapezium formula of area and H. Okay, so where Wm is the specific weight of the masonry and the weight of the dam acts at a distance x from the vertical face BC of the dam. Okay, from BC of the dam. So BC is vertical face. Okay, BC is vertical face. Already we have defined this. Then where x is equal to A square plus AB plus B square upon 3 into A plus B. So actually it is x bar. Actually it is the x bar. So x bar centroid. So already we have studied in the applied mechanics here. X bar is equal to A square plus AB plus B square upon 3 times A plus B. So B cube minus A cube upon 3 times B square plus A square. Okay, this way we got the weight will act at x bar. Okay, so weight of the dam will act at the x bar. Then horizontal water pressure W into H, W into H into H into half triangle. So WH square upon 2. I think it is WH square upon 2. Yes, WH square upon 2. Yes. So WH square upon 2 here, acting at H by 3 above the base. Reaction at the base for the equilibrium of the dam, the resultant of W is vertical because weight is acting vertically here, and P must be contracted by the reaction at the base. Let R be the resultant of the W and P. So this R resultant force because of the weight of the dam and water pressure, but it will act at point Z, which is located at distance Z from the vertical face. Okay, let the line of action of the resultant R meet at the base Z. Resultant R is acting at Z may be resolved into two components as usual, horizontal component and vertical component. Vertical and horizontal components R is acting at Z equal to W and P respectively. Okay, then vertical component W and the force R acting at Z by the normal reaction at the base. by the normal reaction of the beds. The horizontal component P, because of the water here, and force R is acting at Z. Resultant of W and P will act at Z point, denoted by R, resultant force. The friction between the bottom of the dam and the soil on which the dam is resting. There is a reaction. So the vertical component W act at Z is an eccentric load. This Z, that is, it is an eccentric load here. Okay. So let ZC denoted by letter Z here. Okay. The distance of point of application of the resultant force R on the base from distance C. And this is Z. Cz is equal to Z, small z. It is given here. So let O be the middle point of the base. Let O be the middle point of the base. That is this B by 2. B by 2. So therefore eccentricity of the vertical component W is equal to E. E is equal to OZ. OZ, this OZ is equal to CZ minus CU. CZ minus CU. This point, CU. That is Z minus B by 2. Z minus B by 2. Because CO is B by 2 and Z is CZ. So Z minus B by 2. So E is equal to Z minus B by 2. So this way we got the eccentricity or eccentric distance here. Then position of point Z, where the resultant meets at the base can be determined by taking the moments of the component P and W about point C. We will take the moment about point C here. Okay, the moment of W about C, moment of P about C, and moment of R about C. So force R acting at Z consists of vertical component W acting at Z and the horizontal component P is acting at Z. Hence the moment of R about C, remember this, moment of R about C is equal to W into Z. Since the horizontal component P is acting at Z and no moment about C. So therefore equation will be W into X bar plus P into H by 3, this will act at H by 3 is equal to W into Z. So that is Z is equal to X bar plus H by 3 into P by W. Okay. So this way we got this equation. Then therefore the stress distribution on the base means this side CD. Okay, stress distribution on this side CD. First of all we will calculate the direct stress. Direct stress is equal to F upon A or W upon A as usual. So W is equal to W upon B into 1 because we are considering unit length here. So therefore it is W upon B. So this is direct stress. The moment on the base, that is M, is equal to W into eccentric distance. So W into eccentric distance E. So that is section modulus. Section modulus will be 1 into B square upon 6. 1 into B square upon 6. So that is B square upon 6. Already we are studying this thing in strength of materials. So P square upon 6. So this is the section modulus. Extreme bending stress is equal to section modulus. This is section modulus of the base section upon section modulus. That is M is equal to W into E. That is M over section modulus. So M upon section modulus, that is M is W into E and section modulus is B square upon 6. It may be plus or it may be minus. If we take plus, it will be maximum, and if it is negative, it is minimum. So this way we are taking the extreme bending stress as positive negative 6WE upon B square. Okay, then P max. We want to find out the P max here. P max will take positive sign and P minimum will take negative sign here. So whatever the direct loading acting on the vertical side, that is summation of V is equal to, that is W. Here already only W we are considering here. If we take uplift pressure, then we have to take W minus U, effective loading, that we have to take. Uplift pressure is not the today's scope, so that is the scope of irrigation engineering or water resource engineering too. When we'll study that aspect in the gravity dam, that will cover uplift pressure that side. But today's scope is only the self weight of the dam, that is W. So total vertical forces is W. Total vertical space force is equal to W now in second year civil students for civil. So W upon B into 1 plus 6E upon B. So this is the maximum stress at the edge away from the water, means at the toe of the dam, at the toe side of the dam, that is D side of the dam. This is the toe of the dam and this is hill side of the dam, just like a shoe. So toe of the dam and hill side of the dam. So P maximum is equal to W upon B into 1 plus 6E upon B, and P minimum, that is at the water edge, that is hill side of the dam, that is P minimum is equal to PO minus PB, that is direct stress minus extreme bending stress, which is equal to W upon B 1 minus 6E upon B. So this way we can compute the P maximum value and P minimum value. Okay, now let us go for application part of this. So far no question has been asked, but I took this problem from the standard textbook. So let us go with this. Okay, so far I never seen the problem asked in the examination as long as the second year fluid mechanics 1 is concerned, because this is the problem actually of water resources engineering 2. When we check the stability of gravity dams, then we'll go for this design aspect in that particular subject. But in today's subject, will only our scope is restricted only the vertical force due to the weight of the dam only. We don't consider any other forces. Okay, and W. So P is the water pressure and W is the self weight of the dam. That's all we will consider today's in the today's lecture. Okay, on the today's topic. So let us go for the problem. A masonry dam 8 meter high and 1.5 meter wide at the top and 5 meter at the bottom returns water to a 7.5 meter height. So H is equal to, here small h is equal to 7.5 meter. 7.5 meter, and capital H is 8 meter. Capital height of the dam is 8 meter. Okay, and distance, you know that H minus H, that is 8.5 minus 7.5, that is 1 meter. 1 meter we considered as freeboard. The terminology is freeboard. We considered as freeboard. The height of the dam and the water surface level. So maximum water level, MWL. So that is freeboard. Okay, so first of all, yes, the taking specific weight of the masonry and water equal to 22.40 kilonewton per meter square and 9.81 kilonewton per meter square for masonry and water respectively. Now consider 1 meter unit length of the dam. Already we'll consider the unit length of the dam. Find out the weight of the dam. So W is equal to A plus B into the H, height of the dam, into masonry, specific weight of the masonry. Substitute the values 1.5 plus 5 upon 2 into 8 into 22.40 here. So we obtain the self weight of the dam as 582.40 kilonewton. 582.40 kilonewton. Find out X bar value. X bar value A square plus AB plus B square upon 3 times A plus B, that is center of gravity or the centroid. So X bar is equal to 1.5 square plus 1.5 into, substitute the values and we will get 1.78 meter value, X bar as X bar. Then water pressure, P is equal to WH square upon 2, that is WH into H upon 2, yes. So that is WH square upon 2, substitute the values accordingly. So 9.81 into 7.5 square upon 2, it is equal to 28.125 kilonewton. This value we obtained here. Therefore, the distance of point of direction of the resultant force on the base Z is equal to X bar plus h by 3 into p by w. Already we have studied in the theory. So we obtained this z value here as 2.99 meter. When we substitute the values accordingly, we'll get 2.99 meter. So eccentricity z minus b by 2. Remember this thing always. You will come across in final year also. So when we study the water resources to gravity dams. So E is equal to Z up minus P by 2. So eccentricity is equal to 2.99 minus 5 upon 2. So that is eccentricity is equal to 0.49. Okay. Then P max is equal to self weight of the dam. We don't consider any other loading, any other vertical forces. We only just simply considering the self weight of the dam. So W upon B 1 plus maximum stress we want to find out. So 1 plus 6E upon B. Then substitute the values accordingly. So 582.40 self weight of the dam upon 5, that is B, is the width is 5 meter is given here. 1 plus 6 into E, eccentricity is 0.49 upon 5. So 184.90 kilonewton per meter square. So this way we got the maximum stress here. So this value is 184.90 kilonewton per meter square. So this is the maximum value at the toe of the dam. Now let us go for P minimum value at the hillside of the dam. So P minimum is equal to W upon B into 1 minus 6E upon B. So 582, substitute the values 582.40 upon 5, 1 minus 6 into 0.49 upon 5, so it's 47.980 kilonewton per meter square. So this way we computed the maximum and minimum stresses for the gravity dams. Okay, so this is the solution to the problem. Okay. So this completes the topics of all the topics of hydrostatic pressure, and next class I will start with new chapter, that is buoyancy and flotations. There is a appeal to all the students and all the spectators and the audience. If you are new to this channel, please subscribe this channel, Civil Engineering and the Law subjects, so that I can upload more videos for your knowledge and information. So please do the needful. Thank you.